should thank the organizers for a very nice lunch. I think everyone is feeling sleepy now. So this lecture I will try to keep at a simpler level. So as he has already pointed out that there is a question mark, and that question mark is going to play an important role. So here I am going to present a result, a standard result, but I have seen that many people are not aware of this result, but it is something that should be taught in the very first probability course. And it has, I think, deep significance for the way we look at statistics. But it's an interesting result, so let's see what it is. Suppose I give you this number, 3.141592, etc. And I ask you the question, is this a rational number or an irrational number? What's the answer? Is it a rational number or an irrational number? Irrational? Irrational? Well, you'll say, okay, it's irrational, it's pi. But how do you know it is not this? I just said dot, 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 dot. I gave you only up to finite precision. Just by looking at those digits, how can you say that it is irrational? True, it is very close to our favorite number pi, but it could even be this. Maybe all the dot, dot, dots are nothing but 0, 0, 0, 0, 0. In which case, it is actually a rational number. So if I give that thing only up to finite precision and ask, is this rational or irrational? Really, you cannot answer. Rationals and irrationals both being dense, you have seen up to a finitely many spaces, very close to it there's an irrational, very close to it there's also a rational. You cannot be sure. Now there's an entire novel written essentially based on this same idea, The Tale of Two Cities. So if you do not know about the novel or you have not watched the movie, so here's the synopsis, because what we are going to see is basically a mathematical version of the novel. So something like a murder has been committed and one guy has been accused of the murder. His name is Charles Darnay, and it seems that he is going to hang or killed by some other means, he is going to be executed. Then the lawyer presents some other person who looks exactly just a look-alike. Now these two people are actually not look-alike because these are actually the actors and they are different. And they look exactly the same, and so all the witnesses now cannot be certain that they have really seen that guy commit the crime or they have seen this guy commit the crime. And because of that reasonable doubt, he is not executed. So the entire story revolves around this. Two persons looking very similar, so you really cannot decide, is it because of this or is it because of him? Now I am going to give you a statistical version of A Tale of Two Cities. Suppose I show you this scatter plot. X and Y, we have seen such scatter plot so many times. Do you think that X and Y are independent? What do you think? From the plot, you get a plot, something against something, and you will say, oh, they are independent, basically no pattern, it's like a cloud and all those things. They look independent. I am going to say that such a thing can never be said. You can never honestly carry out any statistical test of independence. That is impossible to do. And there's a very simple, so there's a simple theorem with a simple proof just based on first year knowledge that we can use. So you may say that they're independent. I will say that that plot can result from data where not only are they dependent, but Y is deterministically related to X. That is, Y is a function of X. So that is actually a graph of Y being a function of X. It is possible to actually get such a deterministic function. You really cannot say, based on that plot, whether you are looking at this or you are looking at that. That might look surprising. How can that be deterministically related? And you expect some kind of a curve or something, but I am going to convince you it is quite possible, even in that case, that they are deterministically related. So that is the surprising theorem that we are going to state and prove. So roughly speaking, it says, you give me Charles Darnay and you say Charles Darnay is a bad guy. I am going to provide his look-alike, Sidney Carton, and you will not be able to say, you will not be able to tell the difference between this guy and that guy. They will be so very similar. Whatever you can say about that, you can say about this guy also. Now mathematically, instead of Charles Darnay, you give me any two independent continuous random variables, x and y. Any two independent continuous random variables, the condition continuity is important, you give me any epsilon greater than 0. I will produce the lookalike. I shall give you two random variables u and v. In place of x and y, I am providing the lookalike u and v such that condition number 1, u has exactly the same distribution as x. V has exactly the same distribution of y. Look at the distribution function of u and v, the joint CDF, and look at the joint CDF of x and y. They are always within epsilon distance of each other. So if you plot the graph, you will just not be able to make the difference. Make epsilon as small as the smallest positive number your machine can identify. Then in your computer, you will see no difference between the distribution function of xy and the distribution function of uv. Now comes the punchline. However, v is a deterministic function of u. I can always produce that. You give me two independent random variables, I will give you two other random variables such that marginally they have the exact distribution, joint distribution is arbitrarily close to that. Yet, these are independent, and that here it is just the other extreme of independence. Deterministic function of u. Now, no statistical procedure can use any information other than the joint distribution of the data. And the joint distribution is arbitrarily close to each other. No statistical procedure can ever distinguish between xy, even if I give you 1 million observation on xy and 1 million observation on uv, still you will not be able to see any difference between the two, between the statistical behaviors, whatsoever test you design. Yet one of them, one pair is independent and the other pair is deterministically related. So I am going to show why that is going to be the case. And this shows that whenever we say two random variables are independent, you are always using domain knowledge. Somehow or other, you have some intuition that this thing should have nothing to do with that thing. Independence can never be inferred based on data. And that is what actually this shows. Now we shall simplify the proof slightly because we will present it only for when x and y are uniform 0, 1, independent, uniform 0, 1. All other continuous random variables may be reduced to it by using the standard CDF inverse transform, etc. But in this talk, I will focus only on xy being uniform 0, 1. And the proof is very nice. It has a nice geometric intuition about it. That's why I am presenting it. So in this case, what I am going to show is this for uniform 0, 1 case. Now I do not need any two continuous independent random variables. I will be working with xy uniform 0, 1 only. You give me any epsilon greater than 0, then u, v both will be uniform 0, 1 because I am working with xy uniform 0, 1. And this step also simplifies because fxy, the joint distribution function of uniform 0, 1 is just x and this is y, x times y. So this simplifies to this condition. For all xy in 0, 1, f uvxy, the joint CDF of uv, is essentially xy. This minus xy is less than epsilon. Whatever epsilon you give, I can make it uniformly close to that. So the two graphs you can never distinguish. And v is still a deterministic function of u. I am going to show this. And just think about the implication. This says that howsoever much data I give you, you can never infer that they are independent. Suppose someone comes up with a brilliant test and says, say if you give me some data of size 10 trillion, then my test will say that u and v are independent. In that case, I will just give you this type of u and v that are deterministically related. Your test will give the same conclusion for both xy as well as for uv. You never really can distinguish them statistically. So here is the proof. So I am starting the proof. The proof is very nice and geometric. That's why I love it. So first I start with a little question. Suppose I ask you, can you give me two random variables u and v such that both of them are normal 0, 1, but u and v, they are not jointly normal. We know that there are some such examples, some complicated density, you can write that down. So marginally they are normal, but the joint distribution is not normal. So many textbooks give some examples. Here is a little geometric one. So think of the normal city. So just think of the normal PDF like this. Imagine that it is made of a card, and then it is symmetric. This side is exactly a symmetric replica of that side. So pick any 2 points. Oops. Any A and minus A, symmetrically. What I am going to do is, I am going to cut out the central part and going to rotate it. So I am rotating that part. And it fits exactly back in the position because it is symmetric. Even if you flip it, it will fit exactly in the same position. This operation that I did is actually nothing but this particular function. If I call this x, if x lies between minus a to plus a, then I gave it a flip, which means I converted x to minus x, and otherwise I left it untouched. From this situation, you can immediately see that y must again have normal 0, 1 distribution. Because I have again restored this particular shape. So x is normal 0, 1, y is normal 0, 1, but clearly x comma y, they are exactly mathematically related and they are not bivariate normal. So that is one way by which you can actually construct such a thing. And we are going to use this trick in order to prove our theorem. So this is the particular joint CDF of the x and y that I showed. So this is the CDF, and here you can see our familiar normal CDF, the marginal. This is the other marginal. Had this been bivariate normal, you will see a nice surface, but because of that flip, there is a strange dent, something like a dent over there. So it is not jointly normal, but still the marginals are normal. So this trick of taking something using the symmetry and flipping it around is going to be very useful to prove that theorem. So I will start with uniform 0, 1. Now we are going to the proof of the theorem. In case of normal 0, 1, we had one type of symmetry. It is symmetric around the center. In case of uniform 0, 1, this is the density that I visualize as made of cardboard. Just everything is symmetric because everything is exactly looking like everything else. So you have a lot of scope of flipping things around. Suppose I split it up into 4 equal parts. So 0 to 0.25, 0.25 to 0.5, 0.75 and 1. Then each of these pieces are exact replica of each of the other pieces. And I can permute, just shuffle them around, still I will get the same shape. For example, I can do the following. I will take that piece and I will swap it with the green piece. There is no way that you can distinguish this from the original density because everything is same. And I can do all sorts of things. I can take this purple piece and just turn it around. I can swap any of these things because all the 4 pieces are identical. So whatever I do, I will again end up with uniform 0, 1. So mathematically, this means what I did just now is I did if x lies between 0 to 1/4, that is if I am in the green strip, the first strip, I took it to the red strip. Then I added half. If on the other hand I was in this strip between half to 3/4, I took it back by half, and if I am in the blue or the purple strips, I leave it as it is. So this is the new thing. Observe that y has still uniform 0, 1 distribution. Y is a function of x because this is the function. X has uniform 0, 1 distribution. After this transformation, y is also uniform 0, 1. Simply because I moved around parts of the density that are exactly identical. So this is called a shuffle of the uniform 0, 1 distribution. And you can do it all sorts of other things. You can split it into 10 parts and just flip things around. Just any permutation will again give you uniform 0, 1. Now we want to understand this mathematically, not just using the 3D pictures. So initially I start with x and y. Y is equal to x. So I get the 45-degree line. So x is uniform 0, 1 and so is y. So the entire mass is now concentrated along the diagonal. So the entire probability 1 is concentrated along the diagonal. When I did the shift, this is what I did. I took this strip, took it here. I took this strip and took it there. So this is what I did. I took this strip, so this diagonal now moved here, and this diagonal came here. So this is the function, this is the graph of the function y as a function of x. So now this has got quarter mass, this has quarter, quarter and quarter mass. They are sort of scattered a little bit over the over the unit square. Okay, suppose I want to find out, after I have done this, so what is the joint CDF of x and y, say at the red point. It is very easy to compute it because it is important to understand it just pictorially to follow the proof. Suppose I want to find out the value of the joint CDF at this point. Very easy, you look at this rectangle. You look at this rectangle. Have I drawn the rectangle? Yes. You just look at this rectangle, that is all values of x less than or equal to this, all values of y less than or equal to this. See how much mass this covers. Remember, each of these lines are worth 1/4 of the mass. There are 2 lines covered. So here, the CDF will be quarter plus quarter, that is half. The value of the CDF here is half. Given any point, you can do the same thing. Suppose I ask you, what is the value of the CDF at this point? Anyone can help me out? It will be 1/4. So here, you look at this rectangle, you always make it the top right-hand corner, and it covers only this, so the probability is, the CDF is 1/4. Okay, so what I am now going to do is, instead of splitting it up into only 4 parts, I can do it in a more complicated way in the following way. So I start with the y equal to x line. And then what I do is I make the first strip, split it up into further into 4 substrips. And take all those 4 strips and distribute them over here. So this is what I do. So let's clearly understand what I am doing. I took the y equal to x line, so there is no flipping so far. Then I split it into 4 substrips, and I put the first substrip, kept the first substrip here. Second substrip I move here, third substrip I move here, the next substrip I move here. So I scattered them out, separate them out. I do the same prescription for the next one. So always the prescription is this: jth substrip of ith strip will go to swap I and j, ith substrip of jth strip. So this was second substrip of first strip. This becomes first substrip of the second strip. This description is rather confusing, but pictorially it is easier to understand. So let's see what happens in the next step. In the next step, I consider the second strip. I get 4 parts out of it, and I will scatter them after them. I continue with the third thing. I again split up all the 4 things and scatter them all over the place, and the last one. So this gives me one way of shuffling the pieces. Again, by the same argument, after all this shuffling, the distribution remains uniform 0, 1. So that's like the graph. If this is the first part, I leave it unchanged. Otherwise, I do this same thing. So is this clear, the way I am doing it? So I am taking the entire mass focused along the diagonal. The entire thing has been split into 4 squares, 16 parts. Each little part here accounts for 1/16th of the probability. So 1/16th mass is scattered, is uniformly distributed over each of the line, and I have scattered them like this. It's a nice function because in no vertical substrip you will see 2 black lines. So it's a function of a graph. It's a graph of a function. So for every value of x, you can find a unique value of y. That's how I have done it. You could have done it in other ways also. For example, nothing prevents you from flipping this around. There are lots of ways, but this is one way. And the way I have done it in the following. There are 16 squares. What I have actually done is I have taken all the 16 pieces and scattered such that each square gets exactly one piece. That is the main way. So that is the main thing that I wanted to achieve. You could have done it in any other way, that is also fine. This is one particular prescription which will achieve it. I have taken these 16 parts, 1, 2, 3, 4, etc., scattered them in a way such that they are all, every square gets one part. That's what I have done. That is one way of shuffling uniform 0, 1. Now let us understand this again using a 3D picture. So how I am faking independence. So this is our 3D space. So I am going to plot the CDFs, x-axis, y-axis, z-axis. This is the unit square where the drama is going to take place, and this is the thing that you are just now seeing. So that's the unit square. I am going to plot the CDF. If I have really independent thing, independent uniform 0, 1, then the CDF will be just the product x times y. That graph will be like this. It is the graph of xy over the unit square. You see, this is a curved line because it is when x equal to y, it is actually basically y equal to x squared line. That's why it's curved. So it looks like this. This is the CDF of the independent case. This is what we want to fake. This is what we start with. Namely, y is equal to x. Just all the mass is uniformly placed on this. So x is uniform 0, 1, y is equal to x. This gives you a perfect straight line. This is not at all like that independence case. I am going to tweak it. So tweaking, first step. So I have tweaked it using 3 parts. So the prescription that I mentioned, I am applied it for only 3 parts. There I showed it for 4 square things. Here I am doing it for 3 square things. So there are 9 parts. I have distributed according to that technique. So the first strip has been scattered like this, the second strip scattered like this, third strip scattered like this. Now the resulting CDF shows certain dents. Of course, the marginals remain exactly as before. The marginals remain uniform 0, 1, but the joint distribution function shows dents. It is difficult to see it from this projection, so I will just rotate it a little bit. I do not know whether it is any clearer because the contrast is not that good. Okay, now suppose I increase the total number to 5. So now it is 5 cross 5, sorry, 5 square, that is 25 pieces. So I have 5 strips, each split up into 5 substrips scattered using the same prescription. And now this is more finer. There are lots of finer dents. Now suppose I make it 10. Still, this is uniform 0, 1, this is uniform 0, 1, but they are scattered in a finer detail. So this is even finer, but the contrast is not that good here, so it is not clear. So I will bring it back to the original projection, and you will see that now I have really achieved a fine curved structure simply by breaking up the thing. Compare this with our target, namely the uniform case. So this is the target. So you see, they are really close, right? So the 2 CDFs are really close. So I am going to prove now that actually if you break it up into fine enough pieces, then the joint CDF will be arbitrarily close to the independent case. So this is the pictorial representation. Okay, so here is the proof. So in this case I am showing it using just 4 square parts. So I split it up into 16 parts, and this is the original thing that I have split it up like this. I mentioned just now that every square contains exactly one piece. I claim that the CDF that you compute based on this will be very close to the CDF of the independent case. So let's work it out. So here are the points 1/4, 2/4, 3/4, 1/4, 2/4, 3/4. This is unit length. This is also unit length. Suppose I take this point. What is the value of the CDF at this point? Anyone can help me out? It is 1/16 because of that. Okay. Because of that idea, what you do is you take this square and it contains only 1/16th mass, it is 1/16. Now just tell me, had this been independent, what should have been the value here? X times y, it should have been 1/16. So I have really achieved the correct value here. Okay, let's move over here. What is the value here? This rectangle contains two parts, so it is 1/8. What is the ideal value? 1/4 times half, 1/8. In this way, for each of these grid points, this CDF is indeed exactly equal to the CDF value for the independent case. So I have achieved exact equality at least at all the grid points. Same argument. And for this, all that I really needed was I have to scatter the 16 pieces so that each square contains exactly one piece. That's all that I needed. You could very well take this here and take this here. Nothing will change. But everything must contain only one piece. That's all that is matter. So at each grid point xy, we have really achieved the CDF. This is u and this is v. F u v of xy is indeed equal to xy. I want to show that everywhere they are very close. At least at the grid points, they are exactly equal. I need to show that at the other points, they will be sufficiently close. Now the argument that I am going to use, I like to call it the cinema screen argument. Say for example, you have one of those traditional cinema halls where you have this kind of screen that you can lift. So what they do is that they will have strings attached to only finitely many points. They will pull only at those finitely many points. And as a result, the entire curtain must rise because this thing is connected by cloth. So this is very close and this is hanging a little bit, but as long as you manage to pull at all the finitely many points, the entire curtain cannot but rise. So enough to control at only finitely many points. The in-between points will be forced to follow. So this is a very useful argument in analysis when you have to show that infinitely many points should come close to something. Show it for finitely many points and then argue that all the in-between points cannot lag far behind. So this is precisely the argument that I am going to use here, and I will do the following. So pulling at finitely many points suffices. So okay, let xy be any point in that square. If it is a grid point, I know I have already achieved what I wanted to achieve. I have shown f u v xy and xy are exactly same. Okay, suppose it is some point, may not be a grid point. Now what I will do is I will take a grid fine enough. In that case, f u v and xy, they cannot remain far apart because of the following. Because I have taken a fine grid, I will take a grid fine enough so that the values at all these points, take any square, red and blue points of each square, they will differ by less than epsilon. You can always do that because all that you have to guarantee is that the value of xy here minus value of xy here, that should be less than epsilon, which is trivial because since xy is a continuous function, you can always make the grid fine enough such that all these differences are less than epsilon. Okay, now suppose you give me some xy. This is xy, which is possibly not one of the grid points. Look at the particular cell where that point lies. So you look at that particular thing and look at its red and green point. I know that the value of my distribution function is exactly equal to xy at these 2 points. I want to show it is pretty close at the black point also. So what is the CDF value at the black point? It is nothing but the total mass that is inside this rectangle. So it is the total mass over this rectangle. This is definitely smaller than the total mass over this larger rectangle because this is larger. Whatever mass is inside the whatever mass is inside the dashed rectangle must also be inside the blue rectangle. So the blue value must be larger than this. Essentially, CDF is not decreasing. That's what I am using here. Similarly, if I look at the red thing, same argument, the value at the black dot must be greater than equal to value at the red dot. So the value here must lie between the value here and the value there. So just using the non-decreasingness, I had to draw rectangles because I am working in a bivariate situation. So the value here must be less than or equal to the value here, which in its turn must be less than or equal to the value here. So both f u v x y and x y lie between the red and the blue values. Of course, at the red and the blue points, the two things exactly match, I know that. And both of them must lie in between. So I must have, since the red and blue values differ by less than epsilon, so f u v, my CDF, and x y, the independent CDF, they must differ by less than epsilon as well. Okay? So whatever point in whatever cell I take, I can use the same argument. So I have shown for every point, the two CDFs are essentially identically the same. Make epsilon very small as your machine constant, you will not be able to see any difference using a computer. that they are exactly the same CDF. So whatever statistical analysis you can do using your computer based on data on XY will be exactly the same as whatever analysis you do based on data on UV. All the tests will give you the same answer. Yet one of them is independent and the other is actually completely deterministically related. So it is interesting to actually do it using R. So you can actually generate this deterministically related data and see how it looks independent. So this little function is all that you need in order to do this. I have called it scramble. So this does that thing. You take the strip, split it into substrips, and then scatter the substrips all over the place. So in order to do this, let us see what are the informations that we need. Okay, I will finish before time. So I need to know which strip I am in. Suppose I have this X and I am working with, say, only 3 strips. Which strip I am in? I am in the second strip. First strip, second strip, third strip. Which substrip? In this strip, I am in the third substrip. 1, 2, 3. And where in the substrip? Exactly where am I located in that substrip? If I know these 3 pieces of information, in that case, I will just swap strip and substrip. Now it is somewhat difficult to work with all these fractions, 1 over 3, 1 over 3 square, etc. So I will just simplify life by multiplying everything out with n square, so that this is scaled to 0 to 1 becomes scaled to 0 to n squared. Then each strip is of length n. So earlier each strip was of length 1 over n. I multiplied everything with n squared, so this becomes n, this becomes 1. And n square x, so x becomes n square x. So first I will do that. That's exactly what I have done. X is the value that you want to change. N is number of strips and substrips. I first extend it, so I call it extend, n squared times x. So that is my number. Now it is very easy to figure out the strip, substrip, etc. I will just first take its integer value, floor of that, so I get this. And then its position I can take as the fractional part, which is extend the actual value minus the integer part. So this part gives me the position, where in the substrip this is located. This will not change. Then I want to find the substrip. That is easy. Because it is n, I will divide by n and look at the remainder. In this case, the remainder is 2, so I get substrip as the remainder operation. That integer value modulo n. This is the modulo operation in R. And then I have to find out exactly in which strip I am. That is very easy. I just divide it by n and take the floor. That is essentially the quotient and the remainder. That gives me in which strip I am, and that gives me in which particular substrip I am. This gives me the position. And then what do? I recombine them back with strip and substrip swapped. I multiply n with the substrip, not with the strip, and keep the strip same and keep the position same, and finally divide by n squared to bring it back to 0, 1. So that is my scramble function. It is a perfectly deterministic function. That is important. No random number generation is done here, and not a very complicated thing also. It just uses essentially integer division and integer modulo operation, nothing else. So given any number between 0 and 1, this function produces another number between 0 and 1. That's it. Okay, now I am going to apply the prescription. You generate any 1000 uniform random number, x. You apply the scramble function to it, it's a deterministic function, and split it up into 100 strips. 100 strip, and each strip split up into 100 substrips. Do that scattering, that is scramble is doing, and you get y. Remember, y is a deterministic function of x. If you know x, you exactly know y. If you know y, you exactly know x. It's a bijection also. And then plot x and y. So the plot should lie along the graph of y equal to x. And let's look at the plot. This is the plot. Will you ever suspect that you are looking at y deterministically related with x? It just looks like perfectly random x and y. Try out whatever test you have and whatever test anyone can design in the future, as long as it is a statistical test that is based on that underlying distribution, no test can distinguish this from an independent case. So if you look at this in some practical data analysis situation and you say, I think they're independent, the scatter plot clearly shows that they're independent, then you are completely wrong. You can never infer that. It could very well come from perfectly deterministically related random variables. So, well, I am finishing before time. So these are the references. I got this thing. So this, I think, was originally proposed by this, in this place in 1991. I have not read this paper, but I got it from this book, An Introduction to Copulas, in 2006. And I think that this is very important because of another reason also. And it might give rise to some interesting chain of researches, because there are lots of results in so-called mathematical statistics that tend to say things like this. Suppose you have some model which has some weird conditions, like the third derivative must be continuous, this and that, blah, blah, blah. In that case, we can say this is complete sufficient, that is ancillary, etc., etc. So all sorts of mathematical statistics result. Now, any real-life practicing statistician will tell you that these are all bogus. They are of absolutely no practical value, but all the statistical institutes teach those things in a routine way. And no one really can say, of course, these things look mathematical, why not prove these things, what's bad about them? In practice, they seem to be quite useless. No one really does anything with ancillary statistics and complete sufficient, except in very simple special cases. I think one can try to show the following result. Suppose you have some particular property. Suppose you are working with a set of distributions, say for example a set of distributions which I call D, and a subset of that satisfies all your conditions. Suppose there is a subset that satisfies all those beautiful conditions like Cramer-Rao type conditions, etc. Third derivative is continuous, blah, blah, blah. I guess in many cases one can show results like C is dense in D, but then so is C complement. Both these and that is actually dense in the total set of distributions. So when you see any data set, there is no way you can actually say, am I seeing the data from some distribution coming from this or coming from that? Now, traditional books always ignore the fact that there is the C complement. They will only say, well, just assume that your distribution satisfies this, 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 and there are lots of impressive theorems. But a practicing statistician naturally does not start with all the assumptions. We have some data, based on that we want to estimate the distribution, and then we will do all those stuff. Of course, if I assume that all these conditions hold, then those results hold. But based on the data, there is no reason to believe that they hold, just as in this case. If I assume that these are independent, you can do lots of stuff. But based on the data, who told you that they are actually independent? They could as well come from a distribution that does not satisfy any of the conditions. In that case, you cannot actually apply all those nice results. I think that many of those things, so many of these so-called statistical inference results are absolute garbage because of this thing. But I have not seen any research done yet. But this is a very interesting thing that does not really require any complicated argument or anything, quite geometrically intuitive. That at least shows that if you say something is independent, then you are bringing in domain knowledge. Somehow you know, from your gut feeling you know that these two things are independent. You can never say, I have collected lots of data, so I know, I have proved that this is independent. You can never have any honest statistical test of independence. Now you understand why I had that question mark. Okay, thank you for your patience.